To get a thorough understanding of heat, we should start by reviewing the concepts that were previously discussed. For example, in the K3 Earth Science tape under the meteorology section, we laid the groundwork. We talked about the nature of heat. Solids, liquids, and gases are made up of tiny particles, atoms and molecules. And in the case of the solid, the atoms are bound together. When we heat them up, these little atoms vibrate faster. In the liquid and the gas, the particles are moving about. And when we heat them up, they move about faster. This is very important, very basic, because it explains why when we heat a material up, it gets bigger or expands, and when it cools off, these particles slow down, it contracts. In the K3 physical science tape, we looked at heat in two different places. Under matter, when we investigated our senses, we found that our sense of touch is really a sensor of heat, and it's important to safeguard it. And then in the heat section in the physical science tape, we looked in more depth at heat, and we talked about reading thermometers and how important it is to use both scales. Learn to use the thermometers. That's a very valuable skill. The students were also introduced there to the sources of heat. Where does heat come from? Then they went on to investigate conduction, how heat travels through different materials. Now, in the 4-6 section of heat, we're going to investigate further expansion and contraction of materials when they're heated. We're going to look at machines that use heat to do work. We're going to look at other ways that heat transfers, by radiation, for example. And we're going to also look at insulators and see how they're used in everyday life. First, the machines. We have machines that produce heat as an unwanted byproduct. And we have machines that are specifically designed to produce heat, like a toaster or an iron or a clothes dryer. Your students can walk around the house and list as many heat-producing machines as they can find. We also have machines that do work which use heat, like a hot air balloon. It lifts materials off the ground by heating air. And a steam engine. Most of our power plants in the United States use coal and oil and nuclear energy fuel to heat water and turn the water to steam and use the steam to drive a turbine which will make electricity for our homes. If you want to illustrate how a steam engine works, here's an easy and interesting way to do it. Get a teapot, plug one in with a potato so the steam can't come out, and then get a water balloon that sets almost perfectly over the top. Then get the teapot and set it on top of a burner. When the steam comes up, the water balloon will start bouncing around, showing how energy of steam can be used to do work. Whether you're an engineer designing a bridge, or you're just trying to get the top off a jar that's stuck, you're going to be using principles of heat. In particular, the idea that solids, liquids, and gases expand when heated and contract when cooled. Earlier we showed this demonstration with a Coke bottle full of cold air. We put a balloon on it and then heated the air up with our hands or held it under hot water. The balloon inflates. This is gas that expands when it's heated. We want to investigate thermometers because this demonstrates how liquids behave when they're heated. And a thermometer works on the principle of heating up the liquid. It expands. The only place it can go is up the thin, narrow capillary tube. And it can be calibrated to read temperature. Your students can make their own thermometers with a test tube. This test tube is the standard size and it's filled with red water. What we want to do is cut a glass tube up that's about 10 inches long and then put it in a cork. This is a #1 rubber stopper. Be sure and put soap on the glass tube before you push it in. Don't let your students do this. It's somewhat dangerous and this tube can snap, so be careful yourself. To break the glass tube to the right size, because it usually comes in really long lengths, you get a triangular file. Put the glass tube down on the tabletop and make a nice hard score cut in it with the triangular file right on the edge. Find the score mark, hold the score away from your fingers and snap it. If you have any rough edges on the end of the tube, you can get a burner and hold the glass tube carefully over the burner and smooth these edges out. Remember to be careful when you're putting the glass tube in the cork. Your students, each group gets one of these corks with the glass tube in it, their test tube full of red water, and they push the stopper into the test tube. Some of it will overflow. That's the way it's supposed to work. We don't want any air bubbles in here. As they press down on the glass tube, and the stopper, you'll see the level of liquid rising up the tube. Next, they want to get a plain white card and tape it to the back of the test tube, or the glass tube, and mark the level that the liquid's at. Then they can go ahead and heat it in their hands or hold it under hot water. They'll readily see that the liquid expands when it's heated. You can go further and calibrate this by putting it in cold water, measuring the real temperature with your real thermometer, marking it here, writing that temperature down, putting it in hot water, doing the same thing, and then making an even number of divisions between those two temperatures. They will have made their own thermometer. We can go on now and investigate how solids expand when they're heated. And there's some pieces of apparatus you can get at science supply catalogs. One of them is called the ring and ball apparatus, and it's just a ring and a ball. Normally, when they're at the same temperature, the ball goes right through the ring. When you heat the ball up on a burner, the ball, of course, gets bigger and will not fit through this ring. When you're working with this, do it only as a demonstration. Don't allow your students to be working independently with these because they get very hot. And when you're through using it, be sure and douse it in a beaker of cold water to get it back to room temperature before you set it down. There's another thing that all thermostats work on the principle, the thermostat in our house, and if you've ever looked inside one, you see this little coil of wire that's all wrapped up. It's a bimetallic strip. And we can illustrate the operation of this bimetallic strip with this little gadget called a compound bar, or an unequal expansion bar. It's two different types of metals that are bound together. They're brazen together. One of them is brass and the other one is called invar. It's an alloy. When it's heated, the brass expands much more than the invar, and you'll see what happens because we're going to demonstrate this. Get one for your class to look at, and don't tell them what's supposed to happen. Have them just make the observation. The first observation they make is that the thing has two different colors, one on either side. It's silver on one side and gold on the other. And we're going to start by heating up the gold side to see what happens. And right away your class will make the observations that it bends upward when we heat the gold side. But what will happen when we put it in water? Well, let's take some water now and douse this thing in water. Watch what happens. Made some steam, but it straightens right back out again. So there has something to do with the heat, and it comes back to normal. What would happen if we now heated the silver side? Would it go upward or downward? And what is actually happening here? Try and get your students to come up with a conclusion that there's two different metals. One is expanding more than the other. And it's like running around a track. If you're running in the outside lane, you have to go further. If you're running in the inside lane, you don't have to go as far. So if it bends outward like this with the gold side on the outside, it's actually getting larger than the material is on the inside. And since they're stuck together, the only thing that this rod can do is bend. Now, how does it work as a thermostat? Well, let's think of it this way. It's going to bend out this way when it gets hot. So here's a contact. When it's cold, it turns your heater on. It allows electricity to flow through the contact. When it gets hotter in the room, the material bends and pulls away from the contact and turns your heater off. We want to go on now and demonstrate more about the expansion of solids. Here's another good activity you can do. Probably should be done as a demonstration. Get a couple bricks or a couple of chairs and extend a wire between the backs of the chairs, put weights or books on the chairs, or just use bricks like I have here. Suspend a weight in the middle, and I'm just using copper wire. First thing to do is to measure the distance from the bottom of the weight to the tabletop. It's 3 centimeters. Then get your burner and heat the wire. Now, if you're using the wire with the varnish on it, the varnish will burn off. Don't worry about that. Once it's burned off, you can continue to heat the wire evenly. Go back and forth. Heat the wire till it's nice and hot. What do you think will happen? Well, your class should know by now that wire's going to get longer. When the wire gets longer, the weight will get closer to the tabletop. And when I did this experiment, it went from 3 centimeters down to 2 centimeters. So I had an appreciable drop, a certain amount of expansion that was easy to measure. And what happens when it cools? As you would guess, the wire goes back to its original shape and it pulls the weight back up. All this is getting to one thing. We're learning about expansion of solids, liquids, and gases. And we can get back to this jar that we can't get the top off. what are we going to do? We're going to hold it under hot water. The cap gets bigger, the glass stays the same, and the cap comes off easy. And then the bridges, we drive over them all the time and we see those little fingers. It's called expansion joints, little metal fingers that we drive over. It's actually a separation of two big slabs of concrete. When the concrete gets hotter in the summertime, it gets bigger and the little fingers push closer together to take up the expansion in the bridge. If we didn't have these, the bridge would buckle. Let's investigate how heat transfers from one object to another. Heat and temperature are not synonymous, by the way. Heat is measured in BTUs, British thermal units. That's the English system. And it's measured in calories in the metric system. And temperature, of course, is measured in degrees. Think of an object as having a certain amount of heat, energy in it. It's on the top of the hill. And another object, it doesn't have as much heat, and it's down below it somewhere. Just as water only flows downhill, so does heat only flow from the hot object down to the colder object. And as the colder object gets more of the heat and the hot object loses its heat, they come closer together and the hill becomes more gradual. Eventually they come to the same point. Imagine yourself holding a hot metal coffee cup. The heat is flowing from the coffee through the metal into your fingers. Your fingers are down on the bottom of the hill, the coffee is up at the top. And of course, the greater the temperature difference, the steeper the hill. And as the coffee heats your fingers up, your fingers get hotter, and if you don't drop the cup, they'll start to come up closer to the temperature of the coffee. Think of, on the other hand, holding the same metal cup, but this time with ice in it. Here your fingers are up on the top of the hill and the ice is down below, and the heat is now flowing out of your fingers into the ice, trying to melt the ice, bring the temperature of the ice up. And as a result, it brings the temperature of your fingers down and we feel what we call cold. There's three ways that heat transfers through materials: conduction, convection, and radiation. We were introduced to conduction in the K3 heat section, and it's very simply the movement of heat through a solid. Remember that the particles are bound together and they can only vibrate in place. It's kind of like little globs of clay connected by popsicle sticks. That was our model. As one piece vibrates faster from the heat that's going into it, it transfers through the little popsicle stick and makes the next one vibrate and continues transferring this energy without the material moving. And we feel heat down in the end of the bar after a while. Convection is different, and it happens in liquids and gases. And in convection, the material is actually moving and bringing heat to a new location. And radiation, whenever you say the word, everybody goes nuclear energy. But every time you're outside in the sunlight or you're looking at a light bulb, you're getting radiated by rays. Much of it is visible that we see, but some of it, the infrared, is invisible. And we have our radiation detector, our hands or our skin, that actually can sense infrared rays. So we're going to look at these two, convection and radiation, and learn more about them. First, let's investigate radiation. Very simply put, radiation is energy that comes from an object, and it depends on how fast the little particles are moving. If we cool it off, we slow the particles down, it gives off less radiation. Finally, we can get to a point what we call absolute zero, where the particle motion ceases and it no longer gives off this radiation. We want to investigate materials to see if they transmit or block or reflect this radiation. So we can use a light source like an electric light bulb. 150 watts is a good size to use. First, investigate clear things, transparent things like glass or plastic. Then try translucent materials like a piece of wax paper. See if you can feel the heat as it goes through the material. And then go on and try two different types of things, something very silvery and something very dark. First, the dark material. We don't feel the heat coming through, so it appears to block it. And it doesn't feel too warm on this side, but it does feel warm on this side, so it appears to be absorbing the heat. What about the silvery material, the aluminum foil? When we hold it up to the heat source, we don't feel any heat coming through here, but now this side is still cool. This means that this material is reflecting it, just like a mirror would reflect light. Now let's put this into a practical application. Have you ever wondered why styrofoam cups are white? We put a hot liquid in here, we want it to stay hot. So all that radiation we want to keep reflecting around inside the cup and keep it inside. What if we put a cold liquid in here? In this case, the heat from outside, we want to keep that heat out, so we make it white on the outside to reflect that heat off. That way it'll keep our cold drinks cool. A thermos bottle, if you've ever taken one apart, is also interesting because they take into account this radiant energy. Same reason it's shiny on the inside and shiny on the outside, just like a styrofoam cup. But a thermos bottle has an extra added advantage. It's really one bottle on the outside with an inner bottle, and they're sealed all the way around, and they've pumped the air out, so it's almost a perfect vacuum. There's very few pieces or particles of matter inside the space between the two. Because there's very few particles, there's very low conduction between the inside wall and the outside wall. So they've added the extra advantage of conduction here too, so it's a very good insulator. Now the magnifying glasses, it might be time to bring those out again, because a magnifying glass not only concentrates the light from the sun, but it also concentrates the heat from the sun. And if the students are very good at it and can focus that little pinpoint, they can burn holes in black paper. Remember, black paper will absorb the heat better than white paper. Now for a quick little experiment. Different cans with the same amount of water in them, and we'll put 100 milliliters in each can at the same temperature. We've got one that's silvery on the outside, one that's black on the outside, and one that's not only black on the outside but black on the inside too. First we'll measure the temperature, the beginning temperature, and record it. Then we'll put them all in the sun and record it every minute or 2 minutes for about 10 or 15 minutes. Which one will heat up first? Which one will absorb the most radiant energy from the sun? Then we want to try the experiment in the reverse direction. We'll start with hot water in our classroom and watch them cool off. Which one do you think will cool off first, or the fastest? And the best way to do it is to record the results and graph them all together on the same graph. Now let's go on and investigate convection, the final form of heat transfer. In the meteorology section, we demonstrated how air gets heated, becomes less dense, and rises. And we used this little convection mobile to measure the flow of heat upward. And of course, the hotter the air is, the faster it rises, and the faster the little convection spiral turns. Just as hot air rises, so do hot liquids. And we set up these convection currents. As the liquid rises, some new liquid must come in to take the place of the liquid that's rising. You can demonstrate this in your classroom with your fish tank. First mount 2 thermometers, one at the bottom of the tank and one at the top, and fill it with cold water. Throw a few ice cubes in it if you can. Then make one of these little gadgets. This is just a small jar. A baby food jar works fine. Take 2 pieces of straw and bore a couple holes in the lid and stick the straws in, and then seal them off with wax. You'll note that one straw goes up high and starts near the top of the lid, and the other one sets in deep to the bottom of the liquid. Then fill the jar with very hot tap water and put some food coloring in it. I'm using green food coloring here. Fill it to the top, and then put the lid on, and then lower it carefully into your jar of cold water. Watch what happens. You want to disturb the water as little as possible. The hot liquid rises. It goes to the surface and floats on the surface. The colder liquid has to go into the little jar to take the place of the hot liquid. And if you look closely in the jar, you see the colder clear liquid filling up from the bottom of the jar upward as the hot liquid rises to the surface. Wrap up this demonstration by recording the temperatures of the 2 thermometers. In this case, I recorded a difference of 4 degrees C. Go on and investigate the other side of convection currents. If hot water rises, does cold water sink? Let's try that experiment next. This time I filled my fish tank with very hot tap water. And if you don't have a fish tank, like the last experiment, you can do both of these in a large jar with a wide mouth. We want to see if cold water sinks. So our sample of cold water is going to be frozen blue ice cubes. You can make them beforehand. You can bring them to class in a thermos bottle. When we put them in the very hot water, watch what happens as they melt. Much like air rising off the hot pavement in a desert, we see these heat waves. But they're really not heat waves. It's light being bent through two different densities of liquids. In contrast to the last experiment, we now see that the temperature is colder on the bottom. And we also note that there's no boundary layer, no blue food coloring just sitting by itself on the bottom. This is because all the heat in the tank of hot water has dispersed the food coloring. These are experiments that will excite the students, and you know they can do them at home. They can make this apparatus themselves. It's a very good demonstration to show. Now let's go on and investigate insulators. Insulators are materials which restrict the flow of heat, and the best way to learn about insulators is to do experiments with them. There's many different things we can do. Here's some examples. Coffee cups, 3 different kinds. I have porcelain, metal, and plastic. I'll put the same amount of water in each at the same temperature, record it, and then let it cool off. As the hot water cools off, we'll see which material conducts heat most readily. Which one does it cool off in first? We can go on and make our own experiments with styrofoam cups. And let's start with cup A, which will be 1 cup with a certain amount of water in it. Cup B is actually 2 cups in one, so we have twice the thickness of styrofoam and a little dead air pocket down at the bottom. And sample C will be in 3 cups with the same amount of water at the same temperature. We'll do the same types of experiments. Measure, record, and graph the temperature versus the time, and we'll see that the thicker the styrofoam, the thicker the insulation, the better it holds the heat. Now I said something about this little air pocket down here, dead air. That's also a very good insulator because the air isn't allowed to convect. It's not allowed to move, to get out of there and take the heat with it. That's why storm windows in cold climates use that air gap between the 2 panes of glass. Another experiment we can do is investigate the effect of different clothing as to how that would keep us warm. And we'll take some samples of liquid, hot liquid, in small jars. We want to control, so this one will get nothing wrapped around it. This jar here has cotton wrapped around it and held with a rubber band. And notice that I'm also putting a square on the bottom to insulate the bottom from the tabletop. And then my third sample here will have wool wrapped around it. We'll see which one cools off, and we'll learn about how different insulators help to keep us warm. As your students learn about insulators, they're going to be learning about how heat travels, and you can start to show them examples like a hot plate with a beaker of hot water on it. Where does the conduction take place? Like from the metal coils into the glass and then into the liquid that's right next to the glass. And then we have convection taking place within the liquid. And we have radiation from anything that's hot. So as it gets hotter, we feel the radiation. And if you held this beaker up, you can feel the radiation coming from the hot water. Heat is really just another form of light, but it's down in the long wavelength section, down below red, and we can't see it. As we go to shorter wavelengths, we come into the visible spectrum of radiant energy, and we now go from our sense of touch to sense it to our sense of vision, and we investigate light.